All right. So So before we get into network flows, what there is a fundamental problem that we would like to solve using this technique, and that is the bipartite matching problem. Okay. So what is the bipartite matching problem? Given a bipartite graph, let's say G is equal to V1 disjoint union V2 comma E, right? Find a matching of maximum size. In G, right? So this is a problem. Okay. And this, like, models many real world phenomena. Like, you have some jobs, and, you have some machines, and you want to assign the jobs to the machines or machines to the job. So you have a bipartite graph where, one side is the job, other side is the machine, and you want to, find a matching. You have some employee-employer things, right? Relationship, and you want to maximize, maximum number of employees that can be there, and so on. So this problem has a polynomial time algorithm. Slightly try to slightly bigger. Right? This has a polynomial time algorithm, but, like, the ideas are very different from what we have seen. Okay? So we'll see that, okay, what kind of ideas are needed, and actually what we'll do is develop an algorithm for a more general problem, which would imply an algorithm for bipartite matching. Okay, so this is, like, just to keep at the back of your head that, okay, this is one problem that, we are going to solve, which is going to be bipartite matching, right? But before we get there, we'll be actually, solving and defining something more general. And the more general thing is going to be the maximum flow problem. So let's first, think about that. Okay, what is this? What are these things about? So this is about, modeling some transportation networks. So okay, so what is typically a transportation network? You have a source, You have these, these can be roads or something, and then these are the junctions, and then you can go from here to here, whatever, right? Something like this, right? Let's say, and this is T, right? So again, so what the nodes can be like, so these represented as graphs. So this transportation network can be of, like a road transport, road network, or pipeline or something, right? And what would the nodes represent? Nodes represent the interchanges, intersections, or the points of of joints in the in the pipeline system. So suppose this is a road, and this is an intersection where these roads combine and go somewhere else. So nodes are the intersections in the road network, or joints in the pipeline. That one pipe comes from here, another pipe comes from here, they get joined here, and then they get redistributed into these three. Right? What are the edges? Edges are the individual roads or pipes. Right? And every edge has something called an edge capacity, which is capacity of the road or pipe. And what do we want to do? We want to generate some flow. Okay, so there is a source node, and from there we want to get to the sink node. So source node generally will be S, sink node will represent by T, and we want to generate flow here. So again, we'll define these things in more detail, and we want to absorb the flow here. And we want to maximize this quantity, that how much flow we can achieve from S to T, right? So this is the very rough high level idea of what we'll be doing, but we'll be coming to everything formally now. That okay, what are these things and how do we define them very formally? Okay, so let's define what is a flow network first. So definition of a flow network. So a flow network is a directed graph. G is equal to V comma E, right? With the following features. Okay. What do we have? That first is with each edge, right? There is an associated capacity. CE. And this is, let's say, non-negative, right? There is a source node, S in V. There is a sink node, T in V. Okay. No edge enters S or leaves T. at least one edge is incident to each node. And we also assume that C's are positive, C's are integers. I mean, here we have just said non-negative reals, but let's start with integers. Later we'll relax it. Okay. So this is what a flow network is. Basically, just a directed graph. So just like here we have this directed graph, it has S and T. And now if I attach some CE to it, some edge capacities, then you can see that it satisfies because no edge is entering S. Nothing is here like that. No edge coming out of T, right? And there is no vertex with which there are no edges incident. Okay. Good. So, any question about the definition of a flow network? Okay. So, if so, please ask. You can stop me at any point and ask. Okay. Good. So now let's define what is a flow actually. So this is just the flow network, which is basically just a directed graph, which is like where all the vertices have some edges and it has an S and T and some capacities on the edges. Okay. Now what is a flow? So an ST flow is a function f from E to again non-negative reals such that it satisfies two properties. The first property is called capacity constraint. And what does it say? That for all edges, f of E should be less than or equal to the capacity of E, right? And it should be 0, so at least 0. So this is the capacity constraint, which is like, that if we want to put some flow on any edge, it should be at least 0 and it should be less than the capacity of that edge. And what is the second constraint? The second constraint is called flow conservation constraint or just conservation constraint. And what does it say? That if you look at any other vertex apart from S and T, right? Then if you sum over all the edges that are incoming, if you sum the flow, E belongs to delta minus V, let's say, is equal to summation f of E on E belongs to delta plus V. Okay. So delta plus V is set of outgoing edges from V, sorry, incoming edges into V, and delta plus V is set of outgoing edges from V. Right? And so these define what is a flow. Basically, a flow is just a function which satisfies these two constraints. That first is the capacity constraint, that for every edge, the value of the flow should be less than at most the capacity, and it should be, of course, non-negative. And the second constraint says that for every vertex, whatever goes inside basically as a flow comes outside. Right? So, like, if this is V, some V, so this is E1, let's say E2, let's say E3, this is V, again, let's say E4 and E5 are the outgoing edges. So these two are delta plus V, and this is delta minus V, right? So what does this constraint say? This constraint says that f of E1 plus f of E2 plus f of E3 is equal to f of E4 plus f of E5. Right? This is when we write this constraint for this V. And such a constraint will be there for every V that has to be satisfied, apart from SNT. Okay? Now, actually we can, so this is the, in the original form, what is the flow, but let's just, try to write it in another way. So if we generalize, then let's just say that what is the, let's call this quantity actually f out of v, f in of v, right? So let's call it f in of v is equal to summation e belongs to delta minus of v f of v, f of v, right? And similarly, f out of v is equal to summation e belongs to delta plus of v f of v, right? So similarly, now we can define for a subset for S subset of V. Again, we can define f in of S is equal to summation E belongs to delta minus of S f of E, and f out of S is equal to summation E belongs to delta plus of S f of E. And again, this, if this is S, all the set of edges that are going in and going out. So this is delta plus of S, and this is delta minus of S. So there can be many vertices here. Good. Right. Good. So we generalize this for S. And now how can we write the conservation constraint in terms of this? Because the capacity constraint is simple. That is just in terms of that individual flow should be less than the capacity. But the conservation constraint can be write now in these terms. It says that f in of V is equal to f out of V for all V belonging to V minus S comma T. Right? So that is what the conservation constraint is. And the value of F, value of the flow is F out of S. Oh, we did not define here the value of the flow, right? Okay. Do that. I do that. Okay, let me try to do that here. That actually I want to define the value of the flow also here. Let me just try to pull this down as much as I can. Shrink it a bit. And here I want to say the value of the flow. What is value of the flow F? Value of the flow F is Vf is equal to summation E belongs to delta plus of S F of S, right? That you want to just sum all the edges that are coming out of S and take the flow value there, and that is going to be your value of the flow, right? And now value of the flow can be just said to be F out of S in these terms. Right? You don't need the summation. You just want to make it slightly more concise. That you want to say F in of V is equal to F out of V. You just got rid of the summation here, which got absorbed in the definition here. There is nothing like different going on here. Okay, good. So this is what a flow is, and so we have defined the what a flow is. It has two constraints and what is the value of a flow, right? And now we can define the problem: maximum flow. Okay, so what does the problem say? That okay, given a flow network, find the flow of maximum value. right? Let's say find an ST flow of maximum. It's sometimes we might forget to write ST, but it will be understood from the context that whenever we are saying flow, then we are saying that we are talking about an ST flow. Okay. So are the definitions clear? So now we have defined everything that is needed for like formally that is needed for the problem definition. We defined what is a network graph or what is a flow network. So a flow network is just a directed graph. Then we define what is a flow, and then we define the problem that is just trying to maximize the value of that flow. Okay, good. So how do we find this maximum flow, right? So that is the question. That is the algorithm we want to try to develop or we want to develop, right? So there is one thing that that is a sort of a crucial observation or a nice observation, which is that if you divide the graph into two parts, let's say V1 and V2, such that S is here in V1 and T is here in V2, and let's say some edges are crossing, right? So let's call the capacity of this edges is capacity of the cut. Then can we relate the capacity of this cut with the maximum flow value? Any ideas?
Capacity is greater than the maximum flow value.
Say again, sorry. Maximum flow is at most the capacity, right?
Yes.
Yeah. So the idea is that maximum flow cannot exceed, and this is true for any cut, right? Any such cut. So let's represent a cut by V1, V2 for now, right? Capacity of all the cuts V1, V2 such that S belongs to V1 and T belongs to V2, right? So what does this say somehow that, so if we call this, if the minimum capacity is called min cut, so min cut is, let's say, cut with minimum capacity, then what does it mean? That the max flow is less than or equal to the min cut, right? This is what we just observed, that at one point you cannot send more than this. So this is slightly easy to see, but what we'll say is that actually these two are equal, that min cut is also max flow, and hence they'll turn out to be equal, right? And we'll see how this equality holds in the course of next two lectures. So this is the so maximum flow problem. There is this nice structure to it that will come to, that how do we find this min cut or how do we find this maximum flow. But this is a very nice property that we will come to in a short while. Okay. I'm not very formally defining these things. This is just to give you a flavor of what kind of things are there to come. Right. Okay. Good. But let's now go back to the maximum flow problem and try to design an algorithm for it, because that's what we wanted to do. We wanted to find that, okay, we want to send so many things, we want to send as many things as possible through this flow network. How can we do that, right? So So let's first try greedy, right? And see what goes wrong. Of course, I've said already that it does not work, but let's try. Okay. So let's start with F is equal to 0 for all E, right? And then we push some flow from S along some path from S to T, right? As much as we can send, right? So this, what is this flow? As much as the path can take, because we are being greedy, right? And we keep doing till we can find some paths which can take something, right? So as much as the path can take, how much can the path take? This is like, max over E belongs to P, CE, right? This is what the path can do. Good. So let's now take an example and see how this algorithm works or how it fails. Okay? Suppose you have a very small network, you have S, you have U, you have V, and you have T. This edge, you have this edge, this edge, this edge, this edge, and the capacities are like 20.
Sir,
Yeah.
so why should it be maximum over all the edges? In the past, should it not be
Sorry.
minimum?
Right. It should be minimum. Thank you. Yeah, of course. I mean, it shouldn't be the max because the capacity should be defined by the bottleneck. Thanks for pointing out. Okay, good. So this is 20, this is 10, this is 10, this is 20, and this is 30. Let's say. Okay. So suppose this is your flow network, which has these 4 vertices and these are the capacities. Okay. And suppose now the greedy algorithm takes the path P is equal to S U V T. Okay, so this path, this path. Is that marker visible? Okay, fine. Should I use some other color? This. Okay, so suppose we want to take this path. The algorithm wants to take this path. Now, what is the capacity of this path?
20.
20, right? Because that is the minimum edge width. So the algorithm pushes 20 along this. So f of, let's say, SU is equal to f of UV is equal to f of VT is equal to 20. And rest it, so now 20 is done. And now, is there some path on which some capacity is left? Now, the problem is that there are these 2 paths, let's say P prime is equal to SUT and P double prime is equal to SVT. But now there is no capacity left on this edge and there is no capacity left on this edge. So you can't send anything here anymore. Right? And what is the largest value of the flow in this example? What can be the largest
40.
that can?
40.
Yeah.
No, sorry,
40?
30.
How?
30. 30. Yeah, 30.
30, right? So how 30 will be achieved? That here
From
you
the first,
push. Yeah.
from the first SU, we give 20, and then we split it into the 2 QT and UV edges.
You go
10,
20 here, it goes 10 here, 10 here, here again you send 10, and here you send 20, right? So you can verify this that this satisfies the flow conservation, because here 20 enters, 20 leaves, and here also 20 enters and 20 leaves, and total flow coming out of S is 30. So the value of this flow is 30, right? So value of this flow is equal to 30, the one which is written in this color. Okay, good. So somehow we want to reach here from, even if we have got this one, then we want to reach here. And how do we want to reach here? We want to reach here by, okay, so what was the earlier thing? So earlier thing was not this. Earlier thing was what? Earlier thing was that here we had 0, here we had 20, here we had 20, here we had 20, and here we had 0, here we had 0, right? So what do we want to do? We know that there is this path and we want to push things here. So somehow we want to push, like, 10 here. But then here we cannot push 10 more, right? So then we want to, like, push back 10 from here. Okay, so we reduce the flow from here and we keep this 20, and this 10 we push here back on this edge. Okay, and then that 10, when it comes here, it has no other way but to get redirected here. Okay, so we do plus 10 here. So for this edge, we push back sort of. So we make this 10, and now this becomes 10, and this becomes 20, because 10 is coming from here and 10 is coming from here, from this edge. 10 is coming, and this edge 10 is coming now. So here 20 is fine, and now this one becomes 10. So we sort of push back the flow and redirect it. Okay. So this is what we want to achieve somehow in a more general way, right? But we'll see that how that can be achieved. But this is the idea that, okay, if we push something and some, this thing becomes more, if something becomes more, something more is coming out, then can we push back and redirect? Right? That is going to be the idea. Okay. So like here, what did we do? Like, we pushed, like, 10 units on SV, but then became too much coming out of VT. So push back on UV, that is decrease the flow. By 10, right? Then again, now what happens is that, too much is coming into U. So redirect the extra 10 on UT. So, and then the total becomes 30. So from this, actually, we get the idea. So what is the idea? What do we want to achieve? So that we want to do 3 things, like push forward, from S, okay, when capacity is available. Okay. Push backward okay, where places, which are already already full, already carrying flow, let's say, faces or edges, okay, carrying flow. And the third thing is divert the flow. So this is what we want to, these are the ideas that we want to use uh, in designing the algorithm, right? So let's, first look at that. Okay, how do we, formalize this idea? So for that, we define this notion of a residual graph. So how to make this idea formal is the question. Okay, and for that, we define this concept of a residual graph. Okay? So now, given a flow network G, okay, and a flow F, on G, define G subscript F, okay, called the residual graph of G with respect to F. As the following. Okay. And what do we want to say? That the vertex set of GF is equal to same as vertex set of G. That is not a big deal, right? So vertex set is same as G. So this V I use like sort of interchangeably, this V of G actually denotes the vertex set of G. And what is H set of GF? So it is made up of two kind of edges, E1 union E2. Right? So E1 is called, let's say, forward edges. And what is this? E1 is set of edges, E belonging to H set of G, right? Such that the flow value is strictly less than the capacity on those edges, right? Okay, and the capacity of those of E belonging to E1 is CE minus F of E, right? So this is greater than 0, actually. Okay. So this is one set of edges, and then the residual graph has another set of edges, which is E2 is equal to set of VU, the opposite edges, such that UV is an edge in G, right? Such that F of E is greater than 0. Just that. If there is any edge that is carrying some flow, then we want to put the opposite of that as VU, right? So these are the backward edges. Okay, and the capacity of these edges, E belonging to E2 is just Fe. Okay. So why are we defining these forward and backward edges and so on? Because we want to do these two things: push forward and push backward. So when there is an edge that is carrying some flow, so suppose the capacity is CE and it is already carrying the flow FE, right? So what do? We put these two edges in the residual graph. One edge is this and one edge is this. So this edge's capacity is FE. This edge's capacity is CE minus FE, right? That means we can increase the flow along the forward direction by CE minus FE, and we can decrease the flow basically on this edge by the value FE. So we can push back the flow of size FE, right? So that is the intuition, okay? So this also tells that for any, for any edge, E is equal to UV belonging to EG, right? It can result in two edges in GF. Right? And it will, if FE is greater than 0, then two edges. Right? And also there is another thing is that in this graph GF, edge set of GF is at most edge set of 2 times edge set of G, right? Because one edge can at most give rise to two edges. One edge in G can give rise to at most two edges in EG, right? And these capacities of E belonging to edge set of GF, the way we defined above, like this FE or CE minus FE, the capacity is called residual capacity. Okay, good. Now in this graph, in this GF graph, if there is a path from S to T, okay, then we want to push some flow on that. So now let P be a path, or P be a simple ST path. In GF, right? Then we want to push the flow on P. And how much flow we want to push? Let's call it bottleneck of P comma F. Is maximum residual capacity. Maximum or minimum? Again, it should be minimum. Minimum residual capacity on any edge of P. Okay. So we look at this residual graph. What is the residual graph? Basically telling us that, okay, how much capacity we have already used, and in which directions we can send the flow, right? So now this is what we want to do, that we want to show the send the flow along the path P. So let's write that procedure. What is the procedure called? The procedure is called augment F comma P. Let's say, okay, that it is given a flow F and a path P, and it wants to send that flow on that path. So let B is equal to bottleneck of the path of P comma F, let's say. Now for each edge, UV in P, if E is equal to UV is a forward edge, that means the same edge exists in G, okay? Then increase FE in G by B, right? Now else meaning E is equal to, so you have this edge UV, so that means UV is a backward edge for some, not some, for VU in E, edge set of G basically, right? So if that is the case, then what do we do? We decrease FE, right, by B, because we are sending back the flow on that edge now. Okay, and this is end if, and this is end for, and now we return the function f that we get. So this is the procedure which does this job given a path P, and this is called augmentation. And a path in G in a path P or an ST path P in GF is called an augmenting path. Okay. And the result of this is result of augment F comma P is another flow, some F prime, which is a flow in G. So we have not yet showed that this is a flow in G. That, let's say, we'll do in the next lecture, right? But let's just go back to our example and quickly see that what does this do now for the residual graph. Okay, so first we have these S, T, U, and V. So we'll, in the next lecture, we'll do these things. So what were the capacities again? So capacities were 20, 10, 10, 20, and 30, right? And now first what we did, we looked at this path, this one, right? And now we put the flow value to be 20, 20, 20, right? So now what is going to be the, so this is G, what is going to be GF? Okay, so let's quickly draw it. S, T, U, V. Okay. So this edge will not have, any this thing, because here the flow value is 0. So here there will be only one edge. Here there will be two edges. So did we define the backward edges for 0 also? I mean, when it can be 0? Fe is less than C. No. So this is only for when Fe is less than C, then the forward edges exist. Otherwise, they don't exist. So this one does not exist actually, because Fe is not less than C. This one also does not exist because Fe is not less than C. And these exist, right? Okay, here there is no backward edge because there is no E1, right? Okay, good. So now there is a path here in this residual graph. Okay, and what is the capacity in this residual graph? What is the capacity of this? This is its capacity is CE minus FE, and FE was 0. So here the capacity is 10. What is the capacity of this forward edge? This is CE minus FE. So CE is 30, FE was 20. So we get 10. What is the capacity of the backward edge? That is equal to the flow. That is 20. And what is the capacity of this edge? 10, which is C minus Fe, right? So what is the bottleneck? What is the bottleneck of this? What is the value of the bottleneck?
10.
10, right? Because the first and the last edges are 10. Okay. So what do? Then we push the flow of 10. So we increase the flow of this by 10 for this path. This is a forward edge. So we increase this by 10. Now this is a backward edge on which we want to push 10, right? So this is our path, right? But this is a backward edge. And for the backward edge, what does it do? If it is a backward edge, then decrease Fe for the forward edge by B. So the forward edge had here 20 flow value. So decrease it and make it 10, right? So new flow values. So this becomes 10. And for this, now this one becomes, okay, so let me just write in red the new flow values. So this becomes 10. And this becomes 10. This was already 10. This was already 20. This was already 20. And this one, now from 20, we decrease it to make it 10, right? And now we achieve the flow of 30 after we have augmented this path, right? So this is just to give you an example. 30 after augmenting the path. So this is what we'll do actually. That we'll keep finding the path in the residual graphs and we'll keep augmenting those paths to get to the maximum flow. And then we'll show the correctness and then we'll see how this works. We'll first show that, okay, why is this flow that we get F prime? Why is this a flow in G? And then how can we use this to keep doing this to get to the maximum flow, right? So that is what we'll discuss in the next lecture. Is there any question?
By the backward edges of weight 20 in the GF, it should not be, shouldn't it be 30 plus 20? Because flow is coming of 20. We can
Sorry.
descend.
Say
How
again. Sorry.
How the backward edge is coming 20 in the
Backward
GF?
edge, what is the capacity of backward edge? Okay, so for the backward edge, the capacity is F of E. Whatever the flow, and what is the F of E here? F of E is 20 here. Okay, so the capacity of backward edge is 20. How much you can push back on that edge? Right now, 20 is being pushed forward, so 20 you can push back. So that is what is represented by the capacity of the backward edge.
Okay, sir.
Yeah.
Sir, backward, there will be no backward edges for SU and VT because
Yeah. The way we have defined, they don't exist. I have just drawn them in red to write the value of the flow. The way we
it
have
is
defined
because they're full. That's why we are not defining backward edge. What is the reason?
exactly. Yeah, so backward edges are only when actually no backward edges will be there actually for Fe greater than 0. Actually, there will be no forward edge, but there will be backward edges. Sorry, you're right. But those edges, yeah. So there are these backward edges with capacity 20. 20 here and 20 here. Okay. Yeah, you're right. Good. But these will not actually be used in because they will not be part of any ST graph, ST path. They'll not be part of any ST path.
Yes.
Thanks, sir. Yeah. Okay. Any other question? By the way, somebody had asked the question in the last lecture. If that person is still there, I'll ask it again about the ith iteration and in the ith iteration, which edges get updated in the shortest path algorithm, in the dynamic programming algorithm. Is that person still here who had asked that question? I realized that it was quite a nice question and I should address it at some point. Okay, we'll see. If yeah, I'll ask it again in the next lecture maybe, and we'll see. So okay, thank you for coming. We are over time. Any other question? Any other quick question about today's lecture? So of course, yeah. So this I had missed that for SU there will be backward edge. There will be no forward edge because the capacity is full. Okay, if there are no further questions, then thank you for coming. I'll see you guys on Thursday. Thank you.